Now we want to talk about something called stability. So far we have studied about extremal number of certain graphs. And then so far we show the results about Turan density and extremal number of certain bipartite graph. All of them just give some asymptotic estimate on the extremal number. For Turan density, you only care about the asymptotic. So it's a constant multiplied in front of a quadratic term. And we don't care about row of the term. And for bipartite graph, we care about what exponents you get on the leading term, n to the some number, and what's that number. We don't really, care about the multiplicative constant multiplied. All of this is because it's quite difficult to get the exact value of this extremal number. So far, the only exact result we saw was about Turan number. Was about Turan theorem. So that was for complete graph. And let's recall how such thing is proved. Of course, there are many proofs, many different proofs for this Turan theorem. But let's consider the following one. And let's say you have a KR plus 1 free graph. And every time if you have an induced copy of K2 disjoint union is K1. So you have two graphs, two vertices, adjacent and non-adjacent. Let's say you have U and V here. Then what do you know is if you take a neighborhood of U and neighborhood of V, their symmetric difference is not empty. So we know this. And what we can do is the following operation. This is called symmetrization. Sometimes it's called Jacob symmetrization. Is that if U has a bigger degree than V, bigger or equal, then what we do is we delete V and add a copy of U from this graph G. In other words, what? U has neighborhood and V has neighborhood. They are not adjacent. Then how do you change? Is that make this vertex adjacent to the neighbors of U only. And what you know is that the one number of edges does not decrease. Because of this condition, you delete degree of V many edges and then you add degree of U many edges. So it either stays same or it increases. And two is that the resulting graph is still AR plus 1 free. Why? If you just see this part, so if you forget it's one vertex, and this is a subgraph of G, so there are no copy of KR plus 1 here. Okay, so the only possible way that this resulting graph contains a complete graph on r plus 1 vertices is that it uses this vertex. So it should be something like this. But because there are no edges between these two vertex, this clique cannot contain both of these. So it contains B but not U. Okay, but if there is this clique, then we delete this and then we add U. Then there must be also a clique because U and B has the same neighborhood. This implies that there was a copy of this KR plus 1 in the original graph G to begin with, which is a contradiction. So these two holds. Once we have these two, then what? We repeat this results graph with no induced copy of K2 plus K1, which is complete, say, T-par type. So it's not difficult to show that if you have no induced copy of this, then you must be a complete T-par type graph for some T. But as it's KR plus 1 free, this is at most R. And in order to maximize the number of edges, the case is when T equal R and when everything is balanced. So which will prove that the maximum KR plus 1 free graph must be a balanced, complete R-par type graph, which gives a true answer. Okay. And if you see this proof, then what is it like? So you take all KR plus 1 free graph. Then what do you do here? You start from arbitrary graph here. So this point is graph. This is set of all graphs. And each point here is graph. You start with this G. And what? And then you find the next graph. G1, say, which is close to G, but better than G. So here, this was your old graph, and then this is new graph. They look very similar on all parts except one vertex. So these two graphs are quite close. We didn't define the distance between two graphs, but you can already see that this part and this part are the same. Only the local changes are made. The edges attached to this one vertex are changed. So this change is quite local. So even though we didn't put any metric on this collection of graphs, we can kind of see that these are close. So you keep taking this new graph, you can move this. And while you're doing that, you are going to the better graph, in better or equal graph in terms of number of edges. And at some point, you should stop. It should stop. And then that's your best graph out of this whole collection. So that's roughly what happens in here. This is something like the following in some way. So let's say you have this function fx, and then it's the graph of your function, and you want to find the maximum value of this. Then what you can do is that there are several algorithms. You start with some points, and then you move according to some law. Something like Newton's method in algorithm. For example, let's say you start here and then you just take a derivative there and then decide which direction to move. So here, you keep move And then at some point, I mean, you find the maximum point. So these two are analogous, philosophically analogous. Just like what you did here, you move and then you reach at the extremal point, extremal graph. Okay, but this method has some issue in general. Imagine that you have this function, something like this. So its maximum is here. But if you start from here, and then you move as before, so you move small value, you only move very little, and what? Then you are stuck here. At this point, you move to the right, then your value decrease. You move to the left, your value decrease. So you cannot move. Indeed, this is a local maxima. But our global maximum is here. And then from here, there is no way to jump a lot because our movement is local. So it has this issue that it leads to a local maximum. But not necessarily global maximum. I mean, this is more, intuitive and apparent to us. You can see it from visual. But here, we don't have any visual picture on how this space of all graphs looks like. But the similar thing could happen. In this proof, luckily, it didn't happen. But when we are considering about different type of movement and then different class of graph and different parameter, then even if you move this, you make this local movement and then reach at the local maximum, it may not be global maximum. So how do we deal with this issue? The way to deal with this issue, a solution, is taking a good starting point. For example, here, let's say this local maximum value is 3, 4, and this is 10. And if we show that the f of x is smaller than, say, 5, let's say this is when x equal 2, this is when x equal 5, this is when x equal 9, and this is if x is not in the interval from, say, 8 to 10. Assume you know this. If we prove this, then what? Then we can forget about all this because we already know that, let's say, f of 8 is like 5. If we know this, then all other points x out of this interval is not global maximum. So we are not interested in. As we are looking for global maximum, then what you can do is that you start from this point when x equal 8, and then you move this local changes until you hit the local maximum. So assuming you start from arbitrary points in here, And then if you show that no matter which point you start from here, or any starting point x0 in here, it leads to the same local maximum, then the local maximum is a global maximum. Because, I mean, no matter what point you start, you get to the same local maximum, means that it is local maximum in this interval. And then because of this fact, it is then global maximum. So this is for the stability. So this part is kind of called the stability. So we'll prove the following and illustrate how this stability method goes on. So we want to determine the extremal number of C5. For this, let's collect a proposition. So suppose we have epsilon and d, and let's say epsilon is smaller than d. And if G is an n-vertex graph with average degree Dn, then G contains a subgraph G prime whose minimum degree is at least contains a subgraph G prime, say, on n prime vertices, which satisfy this minimum degree condition instead of number of edges. And furthermore, the number of edges in here is at least this. So this expression is not too important, but this is a bit more than this. So this is the original graph has half times t times n square edges. And then here it's proportional. Instead of n, you have n prime. But it contains more here. Essentially, it says that by shrinking your graph a bit, you can assume minimum degree condition instead of number of edges condition. In fact, what it implies is that n prime is at least half times, say, square root epsilon n. Why? If n prime is smaller than that, then if you just compute this, and that's bigger than n prime choose 2. But this is n prime vertex graph. It cannot have more than this many edges. And we will not prove this proposition. And in fact, I mean, this proposition is not difficult. If your original graph satisfies this condition with n being n prime, then we are fine, we are happy. Otherwise, you take a vertex whose degree is smaller than this, and you delete. And then you look at your new graph. If that satisfies this minimum degree condition, then you are happy. Otherwise, you take one vertex with a lower degree and you delete. You keep do that. While doing that, you delete this vertex with a small degree, so you can keep track of the number of edges in the remaining graph. because your deleted vertex has slightly smaller degree than average degree, you keep do that, then you can show that the number of edges in the remaining graph it's kind of increase. So in a sense that its average degree is d prime n prime, but this d prime is bigger than d, and this d prime gets bigger every time, and then you can keep track of it, and you can check this condition. Okay, we have this proposition, and using that, we can prove this stability lemma. So suppose n is large enough, so for given epsilon, let's say delta is small enough compared to epsilon, and then n is large enough. If G is an n-vertex graph, n-vertex 15 free graph, with the number of edges being at least quarter n square minus delta n square, then G can be made bipartite by deleting and most epsilon n square edge. So one of the typical way of measuring graph metric is that if you have this graph and this graph with the same vertex set, so let's consider labeled graph. And you measure the distance between these two by the number of edges you have to change, number of adjacencies you have to change from here to here. If there is an edge and then there is no edge, then you have to change one. And if there is no edge, if there is an edge, you have to add also one. You can measure the number of these changes, and that's the distance between these two. And when your graph is not a labeled graph, but unlabeled graph, then you check all possible different way of labeling. So you can try to map. So there are n factorial ways to make a bijection between these vertices. You check all of them and then measure the distance, and then you choose the smallest distance. And that can be considered as the distance between these two. So in that sense, what this does is that your graph is very close, the distance at most this from a bipartite graph. So if you have a C5 graph with this condition, so in other words, it's like this. If your f of x is bigger than 5, then you must be somewhere here. In other words, if your number of edges is bigger than something, then you should be like somewhere here, very close to this bipartite graph. So this is the stability lemma. So let's prove this. So from this, what do you get? We know that the average degree of G is bigger than say half minus 2 delta, and then we apply the previous proposition. With say delta to the square root of delta in the rho of epsilon, then what? We obtain, so this epsilon in this proposition is how much do we lose by converting every degree to minimum degree. We obtain an n prime vertex graph G prime, which is subgraph of G, with what minimum degree of G prime is at least arc minus 2 delta minus delta to the square root of delta times n prime. And let's write as delta is small, we can simply replace this lower bound with this. Okay, and this G prime is also C5-3. And Erythritton-Simonovich theorem, and the fact that this n is sufficiently large, we know that the number of edges in n, this n prime is bigger than half times what? This. So start to do 1/4 n. So n prime is also large. So this holds. Erythritton-Simonovich theorem roughly determines the exponent number of C5. So this is C5 graph, so it has almost this many edges. And from this proposition, we have this lower bound. This is what? Quarter minus half delta n prime square. 김영우는 quarter low delta? Maybe just delta n square plus half times square root of delta n square minus n prime square minus n minus n prime. And solving this inequality, you can get that the 2 delta plus half square root of delta n prime square is at least half delta n square. Then what? If you divide this, then n prime square is what? 1 over 1 plus 4 square root. This is 1 minus 4 square root of delta n square. The n prime is at least 1 minus say 10 square root of delta n. So G prime has almost same size as G. And what? We know that this G prime contains more edges. I mean, this minimum degree condition holds. This is dense graph. So this contains more edges than external number C4, which is roughly what? Theta of n prime to the 3 over 2. We know that there is a copy of C4 in G prime. And let's say you have this x1, x2, x4, x3, x4 be a copy of C4. And what we do is we consider A as a neighborhood in G prime, common neighborhood of G x1 and x3. And B be the common neighborhood of x2 and x4. And okay. Then A and B has empty intersection. Why? If we have points which is adjacent to all four of them, then what happens? Then we have a copy of C5. Otherwise, C5 arises. Also, by the minimum Dirichlet condition, we know that the A and B have size bigger than half minus 5 square root of delta n pro. Right? So this is disjoint. You have A and B. They are disjoint. Okay, let me explain it this way. So we can further, I'll just omit the subscript. We know that the neighborhood of this and this are empty. Intersection is empty. Otherwise, C5 will write as I mentioned. So their neighborhood is here and here. And then due to the minimum degree condition, outside, it's pretty much everything in G prime, except the outside set has size almost 4 delta square root of delta n prime. And in the same way, so this is like 1, 2. 1, 2 is empty, and 1, x4 is empty. So this is neighborhood of x1. Then neighborhood of x2 and x4 should be in here. In here, you have 2 sets, and then you take the intersection. Then, you can see that it has to be large. And indeed, this could be bigger than 5. And in the similar way, when neighborhood of x2 is fixed, and neighborhood of x1 and x3 must be outside here, and both of them have size at least these, so their intersection must be also large. You can use that to prove this. Okay, and moreover, A and B are independent sets. Why? If we have A, which is the common neighbor of x1 and x2, x3, then if there is an edge here, then what happens? You take this to obtain a C5. So A is independent, and similarly the B is also independent. Then what? If A, B are large, so now we delete all the edges in G which are incident with the all vertices not in A and B. So you have A and B, and then they are independent. It's bipartite group between them because they are independent. And then there are some vertices here in G prime and vertices here in G. And we delete all the vertices incident with these vertices. All the x's incident with this vertex. Then we obtain a bipartite graph. After deleting how many vertices? So because of this and because of that, you have 30 times square root of delta n times, that's number of vertices here, and then each is adjacent to it, n most n. So that's 30 times square root of delta times n square, which is smaller than n square, because delta is sufficiently smaller than n, smaller than epsilon. So this many edges. So this proved the stability result as we wanted. Okay, and now we want to use this to identify the extremal number of C5. And maybe we have spent enough minutes on this video, so I will break it here and then I will continue on the next video.